we do our simulation on our own platform that's written in Python.
Yeah.
So if we prove headquarters that our algorithm better than there, or if we prove that our approach of some kind of process is better than they have by our simulation, they will implement it on their real platform in Java.
And then the programmers will be.
Yeah, but our code will be useful in this case, even if it never will be used on production level. Okay.
Yeah.
Let's start.
Yeah. Can I start, sir?
All who want to visit is here. Maybe someone is online.
Yeah, still we're checking, for example. You can see him.
Okay, so today we have a talk of Anand Mahendran.
Yes, sir. Thank you.
And the title of the talk is on the screen. You are welcome.
Yes, sir. Really.
Теперь вижу. Да, и точно такая же на компьютере есть. И в целом все на компьютере. На компьютере тоже. На ком? Да. Тоже надо включить. Да. Класс. То есть можно там, так. Да. Да, в любом. Стопу здесь. Да. Все.
Can I start? Yeah, okay, fine. So, good evening to one and all. So, my name is Anand Mahendran. I am working as a postdoctoral research fellow in Laboratory of Theoretical Computer Science. I joined as a postdoc in the month of November 2021. So during this 3 months, I have carried out 2 research problems. So one of the research problem is on the generative power of semi-bracketed contextual grammars. So now, so this is going to be my outline of the talk. First, I will slightly give a brief introduction about what is contextual grammars, and after that we will move on to something called as a variance of contextual grammars. Next, slightly I will touch upon the fundamental definition of bracketed contextual grammars. Next, I will move on to the variant which I have introduced called as semi-bracketed contextual grammars, and after that we will see what is the generative power of the new variant with the existing Chomsky grammars, and what is the generative power of the semi-bracketed internal contextual grammars with other ICC grammars. So ICC is nothing but internal contextual grammars with choice, and after giving the generative power of SBIC with Chomskyan and ICC grammars, I will just show you what are all the results obtained, and finally I will project what is the exact hierarchical relationship where we can fit it with other existing grammar formalisms. And in addition to that, I have analyzed some more closure properties of the newly defined semi-bracketed contextual grammars. Finally, I will conclude and what could be the future work. There are a lot of problems are there, which can be considered as a potential research problem, particularly in the domain of contextual grammars, specifically in the domain of bracketed contextual grammars, and with some references. So now coming back to the fundamental definition of contextual grammars. So contextual grammars were introduced by a great computational linguistic by Solomon Marcus in 1969. So the contextual grammars is mainly based on the fundamental linguistic operation of inserting the words. So now here obviously one question is getting arised, how to insert our words. So randomly we cannot do that. So based on some selectors, we are going to adjoin left and right context. So that is the basic operation which is considered as one of the fundamental operation in computational linguistics. So based on this idea, Solomon Marcus has defined one of the fantastic grammars so in computational linguistics. So now to be more precise about contextual grammars, so how the contextual grammars can be defined, how the language can be obtained from a contextual grammars is, we must want to start from a finite set of axioms, and by using the selectors we must want to adjoin the context in an iterative manner. So based on this basic operation, the language can be generated by the grammar. So now here one important question is, this contextual grammars is intrinsic grammars, or we will call it as pure grammars. There is no concept called as non-terminals. Here there is no idea of non-terminals. So that point has given a phenomenal research to be happened. So whereas when we consider our normal Chomsky hierarchy of grammars, your derivation has to start from the start symbol, where we will have the non-terminals. We can have a leftmost derivation, rightmost derivation. So all the derivation will happen only based on the non-terminals. Whereas in contextual grammars, there is no idea of non-terminals. We are going to start from an axiom. So that axiom is going to be purely of symbols. So that point made your contextual grammars to be more precise when compared to context-free grammars. So now, the fundamental operation is adjoining. So that adjoining can happen at the end, or it can happen in between the substrings also. Based on this, two variants has been defined. One variant is external, where we are going to adjoin the context only at the end. And in 1970s, they found this external contextual grammars may not have a expressive power, because we are going to adjoin only at the end. So in 1980s, George Pond and Nguyen has introduced another variant of contextual grammars called as internal contextual grammars. So where we are going to adjoin the context based on some substrings. So now slightly I will brief about the contextual grammar definition. So now here I am not going to touch on external contextual grammars, because my main work is focused only on internal contextual grammars. So now we can see it's a standard definition. We are going to have an alphabet, a finite language, and here this S is called as a selector, and C is called as a context. So now I will try to give one or two examples where we can easily understand exactly what is the meaning of an internal contextual grammars. So the logic is, I don't know to point.
Just worked?
No, just to highlight the pointer.
Yeah, but we're not yet ready reading.
Okay, it's enough, no sir, can I, but I'm not able to get that pointer, so where I can show.
So you should press here on the green button, but it doesn't.
No, it's not, doesn't know, it's not working. Yeah, no problem. Yeah, no problem, so I can manage. So see, the logic is we must want to start from the axiom, and we can take any derivation step, x goes to y. So now here I must want to split that x into three substrings. I must want to split. Here the slide is not, slide changes.
And any derivation is
not
possible. So you need only that x sub 2 is a selector and the pair UV is the context.
Yes, sir, of course.
So no ternary relation between.
No. There is no relation. You take a x, split into x1, x2, x3. Based on that, x2 is a selector. So based on that x, we must want to adjoin u and v. U is called as left to context. V is called as right context. So that's the a simple definition.
Okay. So and for any selector, and for any context, you can increase uv.
Yeah, of course, we can do that.
So.
I'll give an example.
Yeah, it's interesting because. So I also have a question about the previous slide when we had contextual grammars with adding only at the end. Do they generate regular languages?
To generate? They generate?
Regular languages.
Yeah, of course.
And a subset of regular languages.
Subset that can be included in the axiom itself, because it's finite in nature, no?
Oh, okay. So they generate all regular languages.
Yeah, of course.
Yeah.
It's a question in the chat.
Yes, sir.
Yeah, it's a statement. So
how can we see it?
you can see it in the chat.
Two remarks.
I think I can connect to Zoom. I just need
so the question is from Nikolai.
Yes, sir.
The first question was, what is SI and CI?
Yeah.
And I think you answered, but
if you
are not satisfied. Then,
okay.
The question is S and C are ordered or not? I guess it is an ordered pair, right?
Yeah, of course. Yeah, it's ordered pair. Yeah, S stands for selector and C stands for the context. So based on the selector, I need to adjoin the context U and V. Hope I have answered. Now let us take one simple example.
Can you say briefly on the previous slide?
Yes, sir. Yeah.
What is the difference compared to external?
Sir, external, there is no x2. We must want to adjoin only at the end.
Oh, in the end.
At the end. That is the reason external contextual grammars does not deserve much attention, because we are going to adjoin only at the end. Okay. Whereas an internal we are going to do in between a string or in between a sentential form.
And how do you see that regular languages?
Yeah, I'll come to that. So let us take this simple example. Okay, so AB is my V and AB is the axiom. In that, AB is a selector and A is the left context and B is the right context. Now we must want to start from AB. So that 2 down arrow indicates the selector, and in the next derivation step, the one which is marked in red, which is nothing but the left context, the one which is marked in the blue is right context. So I can apply this n number of times. Okay, finally I can get A power n, B power n. So the interesting part here is,
selectors might be infinite.
Sir, yeah, possibilities there, sir.
And you have no restrictions on this infinite subset.
It's a subset of V star over, it's in a V star. We can have infinite number of selectors, possibility is there. But to generate a language, we can do that with the finite set of selectors. You no need of having infinite.
In the example 2, you use a regular set.
Yeah, that is the nature of the selectors, not the number of selectors. Yeah.
Can you just switch on the previous slide?
Yeah, sure.
So we have S, it's a finite subset.
Yeah, of V star.
And C is a finite subset of
V star.
Yeah, and we have ordered pairs of selectors in context. So no, we do not have infinite selectors. We have only finite subset.
It's a finite subset of V star.
Yeah.
C is also finite subset of V star into V star.
Great. And on the next slide, you have an infinite selector. That's why we are confused.
No, sir. It's not. It's a selector. That's the reason I given here. Selectors are, for example, one are of finite in nature. This is of regular in nature.
Okay.
But in the definition, you do not allow infinite selectors.
No, it's not infinite selectors. It's a finite subset of V star.
Yes, but A, B plus C is an infinite subset of V star.
Yeah, so the next example, the second example, is not a contextual grammar. It's kind of an extension.
Yeah, of course.
So it's like, so in the first example, it's clear that if you have finite selectors, you can generate A
power n, B power n. Yeah.
Can you generate A and B and C n in this model?
No, in this model, A power n, B power n, C power n, to generate a triple agreement language, we cannot have a selectors which are finite in nature. You must want to have a selector which are regular in nature. So by using finite selectors, we cannot generate A power n, B power n, C power n. By using selectors which are of regular in nature only, we can generate A power n, B power n, C power n.
We have classical contextual grammars with finite selector. Are they a subset of context-free language?
Now that depends on what type of selector we are going to use. If you are going to use selectors which are of finite in nature, we can give such a claim. But if you are giving selectors which are not finite in nature, which is exactly, we can say, which is power above CF, context free. Yeah.
So one more time, let's fix the definition. So,
yeah, sure.
If we fix the definition so that all the finite selectors are available, then we call it contextual grammars, right?
Can you please repeat the question once? I'm not able to get it.
It's discussion. So we should use the definition of contextual grammar.
In
the previous slide, you allow only finite selectors.
Yeah.
So let's call this object only contextual grammars, okay? So if we allow regular selectors, let's call it somehow else.
Fine. Yeah,
okay. So if we have just contextual grammar, my question is whether the class of the language is a subset of context-free languages.
Yeah, of course, we can generate. By using selectors of which are of regular in nature, we can generate all the context-free languages. In addition to that, we can generate some of the non-context-free languages also. I'll come back to that later.
Okay, I can believe that it's a subset of context-free languages due to pumping lemma. But I cannot.
Can you check the questions?
Yeah.
These are the same questions. It's just
Okay.
Yeah, fine.
From another level.
Yeah, sure. Yeah. Yeah.
Okay, and you cannot generate anything outside context-free languages.
Context-free languages by using finite selectors or regular selectors. That's what my claim. You are talking selectors of finite or selectors of regular.
Finite.
Yeah, finite we can do that. By finite we can generate a power and b power n, which is outside of the regular. But you cannot generate all the languages beyond the power of context. That's not possible by using finite selectors.
Yeah, great.
Yeah.
Can you show the previous slide that
Yeah.
you're sure about the name? Contextual grammar,
Yeah.
it means finite. And when it's regular for the selectors, how do you call it?
Yeah.
No. Again, you see,
So the title is not...
No. I'll come back to that. Right? I'll come back to that. See, yeah, wait. So the selectors, which is there S1 up to Sn. So that selectors can be of finite. That means, okay, if you take Chomsky hierarchy of grammars, okay, you can have the selectors of finite. You can have the selectors of regular in nature also. So we cannot change the definition. So the entire power of these contextual grammars purely depends on what type of selectors I am going to take. Whether I am going to take the selectors which are of finite in nature, or I am going to take the selectors which are of regular in nature. So if I am going
The second example does not fit your definition. And we are confused. You name contextual grammars two essentially different things. Example 1 and example 2.
Yes, yeah. Sir, the point is, based on the selectors, okay, based on the selectors, the expressive power of the contextual grammars can vary. That's what I am trying to mean. If I am going to use the selectors which is of finite AB, okay, so the power of that grammar may fall within the power of context free. If I am going to take a selector which is of regular, the power of the contextual grammar is beyond the power of regular. That's what I am trying to mean.
Give another name for the model with regular selectors and we will be happy.
When
okay.
you will use name contextual grammar in future.
Yes, sir. Okay.
What is the definition?
It's finite or regular, or it can be both. So you
Or maybe you have a more general...
yeah, of course. It can be both.
So
it can
two long names. Contextual grammar with
finite selectors, contextual grammars, regular selectors.
With regular selector. That's how it works.
But in general literature survey, we will define as contextual grammars whenever we are discussing the generative power. So at that time we will say CF with finite selectors, CF with regular selectors.
Okay. So if we have regular selectors, we still inside the class of contextual languages.
Yeah, true. Yeah,
Great.
that's true.
And
So
generate arbitrary context-free language with contextual grammar with finite selector.
Yeah, with finite, okay, we must want to look upon. We cannot give such affirmative statement. With finite selectors, we can do that.
So class of languages generated by contextual grammar is exactly context-free language.
With what selectors? With finite selectors or regular selectors? Yeah, of course.
Oh, it's surprising.
Yeah. So now slightly I will move on to the variants. Okay. So there are lot of variants are there. Okay. There are n number of variants are there. One variant is depth first derivation, maximal local, maximal minimal, and erased context, one-sided derivations. No, I am not going to take all the variants of contextual grammars. I am going to take only 2 or 3 variants. And based on that variants, I am going to study the generative power.
I propose to concentrate on exactly one variant, the most interesting.
Yes, sir. Okay. I am having a lot of results.
It's very difficult to follow many.
Yes, sir. True. Yes, sir. Okay, sir. Fine.
It would be helpful to concentrate on something.
Oh, okay, sir. Fine. First derivation, first variant, which is called as maximal local. So now the logic is very simple. So x goes to y. So if I am going to use that ml in the suffix, it defines I am going to use my selectors in the maximal local mode. That's ML in the suffix. So now if and only if x is equal to x1, x2, x3, I am going to get my y for some selector Si, ui comma belongs to vi. The condition is there should not be any x1 dash, x2 dash, x3 dash which belongs to v star in such a way that x1 dash, x2 dash, x2 dash, x2 dash belongs to Si and x2 dash contains x2. So this is one,
Subword, right?
yeah, of course, subword. It seems to be a little bit confusing. I'll try to give an example where you can easily understand exactly what is the meaning of maximal local. So now I'll switch back to an example and I'll come back to the definition. Now let us take this simple example. So now the language is triple agreement, A power n, B power n, C power n. So this language can be generated by this contextual grammar by using regular selector because there is B plus. So it's not finite selector, it's a regular selector. So the interesting part here is, so this language can be generated by the contextual grammar if I am going to use my selector in maximal local mode. If I am not going to use that in maximal local mode, A power n, B power n, C power n cannot be generated. So now the logic is very simple. Let us start from ABC. Okay, so there is a selector B plus. Okay, the logic here is, whenever I am finding a B plus, the second derivation, there are two B's is there. Okay, there is a possibility of taking that B plus as one B. In between the two B's, I can insert an ABC. So there, after a B, I am getting a A. So that is absolutely not possible because I am going to apply this derivation under a maximal local mode. So the logic is quite simple. Any number of B's are the possible selectors, but under the maximal local mode, the subword which is having the maximum number of B's should be chosen as a selector. So with this additional constraint only, this language can be generated by a contextual grammar mode under maximal local. So the logic is, if I am going to consider this for only one selector, then it is called as maximal local. Now if I am going to consider this for all the selectors, then it is called as maximal global. Now for maximal global, I will give another example where we can easily correlate between maximal local and maximal global. See, from second sentential form to third sentential form, B plus, okay, there is a possibility of inserting between the first B, second B and the third B. So if I am not going to use this in the maximal local mode, this language cannot be generated. If I am going to use in the maximal local mode only, A power n, B power n, C power n can be generated. So the power of contextual grammar is slightly getting increased whenever I am putting lot of restrictions or lot of conditions whenever I am going to choose the selector. So can I go to next maximal global mode? Yeah. Any?
Саша, speak. Решение?
Мне кажется, это Верещагин. А, нет, это кто-то еще. Можно продолжать, мне кажется. Просто фоновый шум.
Yeah, sure. So the next, let us take this simple language. Okay, so now A power n B union A power n B power n. Okay, so this language can be generated by maximal global mode. So now I will clearly differentiate what's the difference between maximal local mode and maximal global mode. So now let us take the first derivation, A square B square. So now if there is a string of the form A power n B power m which presents the subword of a derivation. So there are two selectors are there. One is AB, another one is A square B square. So now in the first derivation also AB is possible. In the first derivation, AB, there is a possibility of having a selector. In the first derivation, okay, so I can choose AB as a selector, possibility is there, but we cannot do that in the maximal global mode. What is the logic is, there are two selectors are there, one selector is AB, another selector is A square B square. So in the first derivation, when compared to AB, a square b square is maximum. So I cannot use ab, I must want to use only a square b square. So this is the difference between maximal local and maximal global. I will go back to maximal local. In maximal local, I must want to check for the maximality condition in only one particular local selector. Whereas when maximal global comes into picture, I must want to check for the maximality condition for all the selectors given. So obviously, when compared to maximal local, we are putting some more constraints on maximal global. So the fundamental idea is, whenever we are putting more constraints on generating or using the selectors, obviously the power of contextual grammar is little bit getting increased. So now this is some more explanation on some of the variants. As sir has mentioned, there are many variants are there in ICC grammars. I have chosen 2 to 3 variants and I compared my study with bracketed contextual grammars. So now slightly right now I will move upon to bracketed contextual grammars. So probably this is a context-free grammar. So context-free grammar has a non-terminal as well as terminal, and since there is a concept of terminals, we are having a derivation tree. So this is a quite simple example. Okay, so a square b cube, I must want to start with a s. S is a start symbol. I must want to choose the first production. S goes to ab, a goes to small a, capital A, and capital A goes to small a, and likewise we can generate the string. So now the interesting part here is, since there is a concept of non-terminals, we can have a parse tree or a derivation tree. But when contextual grammars we are going to take, since there is no concept of non-terminals, we cannot have a derivation tree. So that is one of the drawback of contextual grammars. So that's one of the biggest drawback of contextual grammars. Since we are not having any non-terminals, we cannot give a diagrammatic representation for the words generated. Since we are not able to give a diagrammatic representation, so whenever we are going to deal with mildly context-sensitive grammar formalism, which is going to suit for natural languages or artificial languages or computational linguistics, they found little bit, it's handicapped. So to overcome this, they have introduced, Martin Widay and Pon in 1998, they have introduced 2 grammars, which is in a variant of contextual grammars called as bracketed contextual grammars and fully bracketed contextual grammars. So now, by using these grammars, how they are going to create a tree structure. So that's an interesting part. So the structure, to the strings are generated by associating a pair of parentheses. Now I will try to give 1 or 2 examples where we can clearly visualize how we can visualize strings generated by grammars in a diagrammatic format. So now before going into that, they have introduced 2 definitions. One is Dyck covered string. So probably we know what is a Dyck covered string. Equal number of A's and B's, where we must want to have a matching parenthesis. To be more precise, Oh, it's not working. Let us take this example. This is a Dyck covered string. So there is an equal matching parenthesis. We can call this as a Dyck covered string, whereas this is not a Dyck covered string. Even though there are equal number of open parentheses and closed parentheses, this is not a balanced expression. So there should be equal number of open parentheses and closed parentheses. At the same time, we must want to have in a balanced manner. So this is a well-known Dyck covered string. This is not a Dyck covered string, even though the number of left parentheses is equal to the number of right parentheses. So now, based on the simple definition, so they have given a Dyck covered string. So the logic is, we must want to apply 2 rules if the string should be a Dyck covered. So the first reduction rule is, open parenthesis W should goes to lambda for W belongs to V star also. So let us take 3 example strings, Y1, Y2, Y3, or Y1, Y2, Y3 are Dyck covered strings, because the logic is quite simple. We must want to take open parenthesis W apply to lambda. So finally I am going to get lambda. Whereas they have introduced another definition called as minimally Dyck covered string. So what is the meaning of minimally Dyck covered is, the logic is we should not have, whenever there is a closing parenthesis, and there is opening parenthesis. Here we should not have any string, and under any circumstances this should not happen. If these two conditions are satisfied, we can call that strings as minimally die covered strings. So the string y1 is not minimally die covered. What is the reason is, after b there is a close parenthesis, and after that there is a string c is there, which is not permitted as per the rule 1. And y2, okay, is you take y3. Y3 is not a minimally die covered string, because first the inner brackets can go to lambda, after that ba can goes to lambda, after that I may get such a notation. In between the open parenthesis and closed parenthesis there is no string. Whereas if you take y2, which perfectly matches the two rules, okay, you're not having any condition like this, you're not having any condition like this, okay. So then we can say the language is as minimally die covered string. Now after introducing this, they have given one more projection also. The projection is very simple. Let us take a sample string like this. This is a minimally die covered string, which is nothing but V union. So this is my alphabet, this is my brackets. Now I must want to take this to this. So what will happen is, all these brackets will be turned on to empty. So now I will get a string A, B, B. So now for this string is generated by contextual grammars. We are not having any tree structure, whereas whenever a parenthesis is included, if I am going to introduce this parenthesis, I may get a tree structure. So now obviously contextual grammars has no tree structure. They introduced BAC and FBAC by introducing a pair of parentheses, and they got a tree structure. So so this is the rules to generate a tree structure. I will explain a simple example. So this is one of a string generated. Yeah, sure.
Like for the statement, I didn't get previous slide.
Yeah, sure.
MDCV, what?
That minimally die covered. So that minimally die covered. Okay.
Oh, sorry,
that is MDCFV.
Oh yeah. So okay, I got
Yeah.
it. Sorry, yeah.
Now let us take this simple word. If these brackets are not there, we cannot have a tree structure. So we are having a tree structure because of this brackets. So now how to express this string in a tree format? I must want to start with an axiom. Start from the left to right, find the maximal substring, put it on the left side of the tree. Again I am starting with open parenthesis, create one more branch. If I am getting a closed parenthesis, currently I am in B, okay, this closed parenthesis will be the lambda. Again I am getting open parenthesis, expand the tree. Here I am getting a B, close it. So likewise we can generate a tree format.
Okay.
Yeah.
When we usually have derivation trees,
Yeah.
we consider a word as a result of projection of leaves from left to right.
Yeah.
Here we consider a word like a result of tree traversal from
Top to bottom.
no, so it's kind of
Partial derivation tree or something.
so from left to right,
Yeah.
like
Yes,
Yes.
traversal from left to right.
Yeah, you're also from
yeah,
left to right
so there
only.
are some
Yeah.
issues with centers. So here we always have
Start from.
just we shall go from left to right in DFS,
Okay.
visual way, and
Yep.
this is how we obtain. So you will treat as a language derivated by the structure like the projection, right? So
Yeah.
you just erase brackets.
Yeah, true.
Okay, and so but it looks not consistent with contextual grammars. Because you don't have projection from leaves here, right?
Yeah, that seems to be okay, but when compared in the domain of contextual grammars, okay, since there was no tree structure, okay, so this bracketed contextual grammars and fully bracketed contextual grammars gained more attention. That could be one of the reasons. See, there is no tree at all,
Yeah.
but by introducing this idea of this brackets, they got a tree notation.
Yeah, but so you put 3 because there was no tree before. But I want to put 3 to have a connection with some kind of classical.
Connection with context-free grammars.
Yeah, not maybe with context-free grammars. Maybe it will be somehow useful for programming.
Yeah. True.
Languages.
Yeah.
And derivation trees are useful in many senses, like
sure.
syntactic trees.
Yeah.
And,
True.
In what sense this kind of trees are useful?
No, actually, truly speaking, that is my next research problem I'm working right now.
Great. So we will find the application.
Yeah, of course. So that is one of my future work actually. Yeah. So now I'll come back to the definition, okay, of the bracketed contextual grammars. The definition is exactly same. Only one change here is earlier we will not have this left parenthesis and right parenthesis. We will have left parenthesis and right parenthesis.
Essentially the same
Of course.
as what?
Yeah.
Let us
Yeah.
give a moment to read your definition. So,
Yeah. So any question?
I think it's just someone speaking.
Okay. Oof.
okay, so we have kind of insertion systems. The same, but now
What's PRPX?
Yeah. That's the last one. Projection. This projection mapping. Which is I mentioned, no?
Brackets.
Just erase the brackets. That's it. Any questions, sir? Any question?
So when you do insertion, you put brackets
Yeah.
around,
Yeah.
right? Okay, and you treat with the results import as a projection.
Yeah.
And,
True.
okay, but so you do not allow selectors contain brackets, right? So you have a kind of 3 restrictions, right?
Yeah. True.
That's why you will have a well-formed word. So it will always be a kind of good Dyck word. Dyck word. Okay. But I think you should also add that your axioms should be surrounded by brackets.
Which one? Pardon? Can you repeat?
So if you have an axiom, it should be, axiom is a word, right?
Yeah, of course.
So you shall surround the axiom
Brackets.
by
Yeah.
brackets.
Yeah. True. And the interesting part here is here we cannot have a selector of lambda comma lambda. So that's the quite interesting part here. We cannot have a selector something like this, because if that is the case, this rule, okay, the second rule might be violated. That second reduction rule. Sometimes there is a chance I may get that empty string, which is not possible.
Yeah, and will you obtain always minimally Dyck counts?
Yeah, of course. It has to be minimally Dyck covered. So that's the interesting case. If x is minimally Dyck covered, my y also should be minimally Dyck covered. So that is the interesting proof Pan and Martin Vide has proved in 1998.
Nice.
Yeah. So now coming back to the fully bracketed contextual grammars, the logic is very simple. Okay, it is exactly similar to your BIC grammar, where in your BIC grammar we are taking the projection for selector, whereas in a fully bracketed contextual grammar we should not take the projection. Directly I must want to take my selector as minimally Dyck covered of you, and I must want to proceed further. So now the interesting part here is, if x goes to y is a derivation step in a BIC or FBIC grammar, if my y should be minimally Dyck covered whenever my x is also minimally Dyck covered, in such a way that since all the axioms are in minimally Dyck covered, any words derived from that axiom will be minimally Dyck covered. The logic here is x goes to y, x is minimally Dyck covered, my y is also minimally Dyck covered, and I am going to start anything from axiom, my axioms are also minimally Dyck covered. So this is it's quite a big proof. Okay, so I am not going to derive this proof. because this is not actually my work. Okay, so right now I am giving only the definitions. So now here we found one drawback. Why the selector should be always minimally Dyck covered? So that is where we have got a hint. Okay, so the logic here is, I'll try to write it. See, the logic here is x, I'm going to derive y. My x should be always minimally Dyck covered. Definitely my y also will be minimally Dyck covered. The most interesting case is my selector, my x2 should be always minimally Dyck covered. So here we got the clue. Okay, what is the clue exactly we got is why the selector should be always minimally Dyck covered. My selectors can also be non-minimally Dyck covered. At the same time, we are maintaining this relation also. So there comes the real hint. So rather than taking my selector as minimally Dyck covered, the variant what we have defined is the selectors can be non-minimally Dyck covered, but this relationship will hold. So irrespective of the selector, whether it can be Dyck covered, minimally Dyck covered or non-minimally Dyck covered, we will hold this relationship. So we have introduced a new variant called as semi-bracketed contextual grammars. So now before moving on to that, the BAC and FBAC grammars, again this is also one of the drawback. So BAC grammars and FBAC grammars cannot generate all these three basic non-contextual languages. It cannot generate cross-dependency, it cannot generate multiple agreements, it cannot generate mocked duplication. So we have found something is missing, okay, in bracketed and fully bracketed contextual grammars. Even though we are having a tree structure, but since majority of the languages, natural languages are beyond the power of context free. Even if we take English, English also is not, it's beyond the power of context free. We found that something is missing. Okay, so even though we are having a tree structure, by using this BAC and FBAC, you cannot generate the three fundamental non-context free languages. So we got a hint, we have relaxed the condition. We have relaxed this condition for x2. Instead of having minimally Dyck covered, you can have a non-minimally Dyck covered strings also. And we have introduced a new variant called as semi-bracketed contextual grammars. Okay, we have introduced this in 2011 actually. Okay, after that we have concentrated on some other problems. We are not able to solve on this. So I have solved all the relationship with internally ICC grammars and SBAC grammars in the last 3 months. So now coming back to the definition. Okay, so we have found the definition to be little bit not complicated, little bit tricky. Okay, so that tricky definition I will give it right now. Okay, so this is the basic definition of semi-bracketed contextual grammars. Everything is exactly same. We have relaxed only one condition, whereas in your BAC or FBAC, your selector should be always minimally Dyck covered strings, whereas the variant what we have defined, it can be minimally Dyck covered. At the same time, it can be even non-minimally Dyck covered strings also. So now, up to that first part, we have found it's very simple to define. But this part we have found very difficult. How to prove this actually. So this is quite simple. We can take this as non-minimally Dyck covered and we have defined a variant. But how to prove this? If x is minimally Dyck covered, my y should also be minimally Dyck covered. Because in the earlier variant it's very easy. Because x is equal to x1, x2, x3. Apply a word. I am going to get y is also minimally Dyck covered. Whereas here we have released the condition. How we are going to maintain this?
But shall the selectors still be Dyck covered? Maybe not minimal.
Which one?
You claim very
No. It should be minimally Dyck covered.
Are not balanced these selectors.
Okay, so SI can be just any word, right?
Pardon? Yes, sir?
SI can be arbitrary word over V.
Yeah, of course.
Union B. Output,
Yeah, of
right?
course. The only condition.
But we have a restriction on x1.
Yeah, but you shall.
It's a completely different rewriting rules. Before we use only conditions on x2 and ignore the structure in xy and x3. And now we require that x1 should satisfy some requirement.
Some format.
Some format
Yeah.
requires,
Yeah, of course. So this took us a lot of time for us to fix this problem actually. So this is one condition. So like that we had 4 more conditions. So now if my selector ends with the bracket and if it starts like this, my x1 should be either like this or like this. If not, I may land in a word which is not MDC in nature. So this is condition 1 and condition 2. If my selector starts with open brackets and if it ends with y, again I am putting some condition on x3, either this or that, in order to maintain this. The third condition is if my context is one-sided, that means if the right part is lambda, I must want to have a selector like this. If fourth condition, if my left part is lambda, I must want to have a selector like this. So really it took a lot of time for us to fix this issue because
so each selector contains only one bracket. Either left.
No. You're talking for which one's the condition 3 or condition 4? It's V union B plus I can have any number of brackets, any number of V.
B any brackets.
Yeah, B is brackets actually. Okay. So now, what is the need for this condition? So why we need this actually? So conditions C1 and C2 mainly needed to fix the format of x1 and x3. So likewise, conditions 3 and 4 are mainly used when the contexts are one-sided. So now, why we must want to impose these many conditions? So the only purpose of maintaining all these conditions is to maintain this. If my x is MDC of V, my y should also be MDC of V. To maintain this only, we have introduced a lot of conditions if my selectors are non-minimal Dyck covered strings. Yes?
Yeah, I have a question.
Yeah, sure.
Assume we have the definition.
Yeah.
You allow any kind of
Selectors. Yeah.
And Cs.
Context.
So, but such that whenever you have a derivation step,
Yeah, sure.
it maps
Yeah.
minimal cover, just do cover string to do cover string. Assume
Yeah, minimal Dyck covered string. Yes. Yeah.
So assume you have such a definition of Cs.
Yeah. Yeah.
And do your axioms cover all such grammars?
You're talking about x1 or what?
Assume we have another kind of definition. So someone give you the system, right?
Okay.
The grammar.
Yeah.
And he claims that in this grammar, this relation on x, gy hold.
This one?
No, on the board.
Yeah, this one. Yeah.
So this one.
This one, yeah.
Yeah. So the question.
Yeah.
Does this grammar fuse to your axiom systems?
Action of these.
Axioms. Yeah. So do the axioms hold for any grammar with such property?
No, it can hold, but these conditions should satisfy. No, I must want to satisfy the conditions C1, C2.
Yeah.
That purely depends on the selector. No, that we cannot claim for any random grammar. It has to satisfy the conditions of x1 and x3. So then only we can fit that into this grammar. Otherwise, it may fail. We cannot guarantee that it may work for all the conditions. No.
Okay, so
Yeah.
we can still kind of extend the definition, the class of these
Okay.
grammars, satisfying these well-formed bracket properties. Okay, and what kind of class of formal languages do you have in this essay?
That is the next what I'm going to project actually. That's what my forthcoming results. Yeah. So now this is some of the examples, okay, where it may fail. Okay. So what's the time?
Yeah, it's okay.
Okay. So can I go a little bit fast because I need to explain the results what I got.
Okay. But you also shall understand something.
Yeah. Sure.
We are already in trouble. Because we cannot keep in mind.
Yeah, of course. A lot of definitions. True.
Yeah, so
See, the first rule, okay, you take D, close parenthesis, alpha is my left context, beta is my right context. See, I am having a string, okay, left parenthesis A, right left parenthesis B, and so on, so on, so. There I found, okay, a selector which exactly matches. So now, what the condition says, if I am going to have a selector like this, my x1 should be either like this or like this. So whereas in the example, after a close parenthesis, I am having a C. Because of that condition, the resultant string does not matches to MDC of V.
Yeah, the idea is clear. So you describe all the cases.
Yeah.
And the well-formed brackets.
Yes,
can
of course.
be,
True.
Yeah. So the idea is clear.
Yeah.
But it's also not clear why don't your axioms describe all such cases.
No, axioms, okay, axioms should be always MDC of V. We're talking about from where we need to start. Instead of having yeah.
Not axioms, but rewriting rules. You mean rewriting rules?
So there are axioms in two senses. So
Okay.
in one sense, axioms is finite words.
Yeah, starting where I need to start my
Yes.
derivation.
And
Yeah.
another sense of axioms
Yeah.
is your conditions, condition 1, condition 2, and so on.
No, that condition is not for axiom. That condition is for having a selectors.
So
It's not for axioms.
You know, piano axioms. You have list of conditions. If they hold, then you have natural round.
Of course, true.
You have your 5 conditions, right?
Four
And you have
conditions.
4 conditions.
Yeah.
They are axioms for well-formed
Yeah, true.
rules.
Yeah, of course.
And this is the question whether when you have your rewriting system, any rewriting systems of your form, such that this relation on x and y,
Yeah, true.
it follows that all your 4 conditions hold, right?
Yeah, of course.
Okay.
And again, one more important part needs to be analyzed here is this z. If I am going to split like this z should be always V plus. If it is V star, there is a chance of getting a non-minimally Dyck-covered string. So it's quite clear. So again, an example. Okay, so there I found a selector like this. If I am going to introduce lambda comma beta, and it's quite clear that it says that z should be always V plus. But in the above example, z belongs to V star. Because of that, I am getting a non-minimally Dyck-covered string. Now, coming back to the results. Okay, so the family of languages generated by SBAC grammars. Okay, we will call it as SBAC of F. Now I'll try to give one example. Okay, exactly how your semi-bracketed contextual grammars works. So this is one example where we can generate, okay, the crossed dependency language, and this is another example, okay, where we are generating another language. So here again we found, okay, one what we can say, a gap. Okay, so this grammar, it's a normal grammar, semi-bracketed contextual grammar, whereas you can see here this grammar is maximal semi-bracketed contextual grammars. So this language can be generated by a semi-bracketed contextual grammar if I am using that maximality condition. So now obviously we have found one interesting and important observation. What is the relationship between SBAC of regular and MSBAC of regular? So this is semi-bracketed contextual grammar with regular selector. This is maximal semi-bracketed contextual grammar with regular selector. So when we have defined the variant, at that time we didn't notice this. Okay, we thought, okay, this can be a subset of this. Okay, this can be a subset of this, but we are not able to give a rigorous proof for that. So we have given, okay, one claim. Okay, only one way we can prove it. There is a language which can be generated by maximal semi-bracketed contextual grammar with regular selector, which cannot be generated by SBAC of regular. So the vice versa, we cannot prove it. So we have just left it as a open problem. Okay. So now again we have took one of the fundamental language which is a non-CFL, a power n, b power n, c power n, and this language can be generated by this simple SBAC grammar, but with regular choice under maximal mode. The logic is very simple. So we have took this word, and here whenever I am finding a b, so I must want to introduce that AB after reaching all the b's on the left side. So because of this maximality feature only, I can generate a power n, b power n, c power n. If this maximality feature is not there, in between these two b's I can have a AB. So obviously at some point of derivation I may get a power I, b power j. After that I can have a power k, which just not belongs to the language. So now so this is a sketch of the proof. Okay, so assume that this grammar can be generated by an SBAC grammar with regular choice, and we are given by proof by contradiction. Okay, since the language has equal number of A's, B's and C's, obviously I must want to have a context, either left side a power I, b power I, for right side should be c power I for a finite I, or other possible contexts. So these are all some of the possible contexts. So now I will try to give the proof for one possible context. Like this we have proved for all other possible contexts, and the proof is very lengthy. So I will try to give for any one context. So likewise we can prove it for all other contexts. Now I will prove it for this context, a power I, b power I followed by c power I. So now let us assume at some point of time I am getting such a string like this. So x2 is my selector. To the left of this I am adjoining a power I, b power I. To the right of this I am adjoining c power I. So now since the language is having equal number of a, b and c, and their order is also very important. So randomly I cannot insert. I must want to insert a, b followed by c. So definitely the grammar should have a selector of this form. So obviously this x2, it can be either a b or a c or a close parenthesis or a open parenthesis. So obviously it clearly suggests that even though my selector is of a regular in nature, we cannot do it randomly. Okay, so I must want to find the leftmost b and I must want to insert, otherwise some point of time I may get such a string like this. Okay, after a b I am finding a because since I am not using this regular selector in the maximal mode, there is a chance of introducing a between two b's. So obviously we can conclude this language, this string does not belong to the language of triple agreement. It's quite simple that we can conclude this grammar cannot generate a power n, b power n, c power n by using regular selectors if I am not going to use in the maximal mode. So likewise similar argument can be given for this context, and for the remaining context also we are given such a similar argument. The argument is exactly same. The fundamental idea is whenever I am finding a word, that selector should be always I must want to go for the maximal length. If I am not going to put that maximal length whenever I am going to derive a word, obviously at some point of time we may land in a word which does not belong to the language. So now these are all some of the possible contexts. So obviously finally we are concluding that this language cannot be generated by SBAC of regular. So this is quite a straightforward result. Since finite is strict set of subset of regular, we are having a power n, b power n, c power n cannot be generated by SBAC with finite choice. Now we will come to analyzing of SBAC grammars with Chomskyan grammars. Okay, so this language it's a not regular language, a power n, b power n. So this language can be easily generated by an SBAC with finite choice. So this derivation is quite simple. Starting from AB, apply this n number of times, I can get a power n, b power n. So this language can be generated by a SBAC grammar with regular choice, but the vice versa is not true. Okay, so there are some regular languages which cannot be generated by SBAC of finite. So that language is regular. So A star, B, A star, B, A star, B, A star. I am going to take the clean plus of that. Okay, obviously that language belongs to the class of regular. The quite interesting part is that language cannot be generated by a SBAC of grammar with finite choice. So the logic is simple. Since between A's I can adjoin my A's either on the left or on the right, okay, I can have, my grammar should have a selector of this form. The interesting part here is I cannot have a selector of this form because it exactly contracts the definition of the SBAC grammar. If I must want to start with the left parenthesis, my left context should not be empty, whereas it happens here. Likewise, if I am going to end with the open parenthesis, close parenthesis, my right context should not be empty here. So this exactly contradicts the definition of a SBAC grammar. And since the number of B's are increased in triplets, okay, so quite simple, from the language we can see each and every time when I am going to take the concatenation, I am going to increase my B's in triplets. So obviously my possible context should be, I can have 2B followed by a B, 1B followed by 2B, lambda followed by triple B, or a triple B followed by a lambda. So we have here I have given a proof for one possible context. Okay, so like this we are having for all the possible contexts we are given the proof, but here I am trying to give the proof for only this format. Okay, B comma B comma B. So now let us take x goes to y, y goes to z. Okay, so this is my in k plus 1th derivation. I am using this context. I am having a B and a B. In the next derivation, again I am going to do the same thing. Here I am going to have a BB and a B here. Now the interesting part here is, now let us take that substring. So here we are having a substring, okay, which is available there, left parenthesis BB, left parenthesis BB. So now since A can be inserted anywhere in the string, so definitely I must want to have a selector which is there marked, which is an arrow, which is not at all possible, because according to the definition of SBAC grammar, my selector either should be of this format or it should be of this format. The most interesting condition here is my y belongs to v plus, which exactly contradicts. So obviously we cannot generate a string, okay, by SBAC of finite choice which exactly matches A star B A star B A star to the whole plus. So like this, okay, we are given argument for other context also. A similar argument can be given for all other possible contexts. Here I have given for two contexts. Okay, one is for BB comma B, and other argument is for lambda comma triple B. The same way how we are given the proof here, we can give a similar argument for all other possible contexts, BB comma B or lambda comma triple B. So finally we can conclude, okay, by contradiction, this language cannot be generated by SBAC of fin. Next, we have analyzed with linear languages. So now that language A power I, B power I, C power J, D power J is not linear. Okay, so that language can be generated by SBAC of finite choice. Again the logic is very simple. Okay, so having a AB, adjoin AB, having a CD, adjoin CD. So I can do this n number of times and finally I can get A power I, B power I, C power J, D power J. This language is not linear, and we have proved the vice versa also. So linear, there are some languages which are linear which cannot be generated by SBAC of fin. So earlier we are given one regular language. Okay, since regular is subset of linear, so that language is also regular, and earlier just before the previous theorem only I have proved. So this language L3, which is nothing but L2 of plus, cannot be generated by SBAC of fin.
But can you say if SBAC of fin is a subclass of context-free languages?
Subclass?
Of context-free languages, or they can generate some non-context-free language?
No, under maximal mode only we can do that.
Okay, so if they can generate only context-free languages and not all, yeah, it's quite. You're okay about linear languages?
Yeah.
So it's just kind of non-trivial subclass of context-free languages.
SBAC of fin, you're talking SBAC of finite. Yeah.
Yeah. Okay.
So now, one more interesting part actually we have derived in this. What is the logic is, let us take, I will try to give for one example. We have proved this SBAC of finite minus linear is not equal to phi, linear minus SBAC of finite is not equal to 5. So what we have proved is both the languages are incomparable, and the interesting part is what we have found it, there are some languages which is common to these both. So what we found out is these two are incomparable but not disjoint. These two languages, these two class of languages, SBAC of finite minus linear, linear minus SB of finite, both are incomparable but not disjoint, because we found one common language. So L phi is equal to a power n b power m. So that language is regular, it's linear, it can be even generated by SBAC of finite. So both these languages are incomparable but they are not disjoint.
Yeah, but it's quite obvious
Yeah.
because every regular language is
of course linear.
So,
Yeah.
And you can generate a linear language vs.
True. True. And so far I have analyzed the generative power of SBAC with finite choice. Okay, so I have not considered regular choice. Still regular choice, still lot of proofs I am working out. So probably I may submit another paper, okay, to any other journal based on regular choice. So now next work what I have carried out is generative power of SBAC grammar with ICC grammars. So I'll come internal contextual grammars with choice, ICC grammars. So the earlier one.
So the first one, right?
Yeah, the first one what we are given. Yeah.
So just contextual grammars. Right?
Yeah. I have not considered that external. I am just considering only that internal.
Yeah, I see.
Yeah, true. I see. So now this is where I stopped. Am I right? Yeah. So now. Okay. Just a minute. So here, okay, I have took three class. One is ICC of finite. Another one is maximal local ICC of finite, and maximal maximal global ICC of finite, and SBAC of finite. What is the relationship between all these four classes of languages? Okay, so again, okay, we have proved that, okay, SBAC of finite with ICC of finite both are incomparable but not disjoint. Likewise, we have proved SBAC of finite and maximal local are incomparable but not disjoint. SBAC of finite with the maximal global are incomparable but not disjoint. So for each and every case we have proved in terms of languages. I'll try to give a sketch of the proof. Okay, so the first one, okay, the first theorem is SBAC of finite. So SBAC of finite minus ICC of finite. The logic is ICAC of finite minus SBAC of finite. This is not okay. So likewise, I have proved for all other existing cases also. So the logic is very simple. The language, there is one language which can be generated by this, which cannot be generated by this. There is one language which can be generated by this, but it cannot be generated by this. And there is one common language between these two classes. So this is what we have proved. So the first proof says one language belongs to SBAC of finite. Other one does not belong to SBAC of ICC of finite. The other part of the proof, there is one language which belongs to ICC of finite and does not belongs to SBAC of finite. So again, there is one language which belongs to SBAC of finite, which does not belongs to ICC of finite under maximal local. So vice versa, the languages are it's not simple languages. So likewise, one more proof, ML local ICC with regular choice. So the logic is same. So we have took, instead of finite selectors, we have took regular selectors. That's all. So instead of maximal local, I have chosen maximal global, and we have achieved this result. So likewise, maximal local global of ICC of regular with the SBAC of regular, we have proved this. And similarly, okay, SBAC of instead of going for finite choice, I have chosen regular choice, and I have obtained this result. And one more variant also we have took. We have took ICC under leftmost derivation, and we have proved in the same manner. And this is some of the glimpse of the proof. Okay, some glimpse of the proof. And so this is for the argument for case 1 and case 2, and the reverse part of the proof. And so these are all the results I have achieved. So first one is SBAC of finite is incomparable with ICC of finite but not disjoint. SBAC of finite is incomparable with maximal local of ICC under finite but not disjoint. SBAC of regular with maximal local of regular but not disjoint. SBAC of regular is incomparable with MGCC IC but not disjoint. ICC of left is incomparable with SBAC of finite but not disjoint. So these are all some of the results what I obtained for this paper, and this is the exact hierarchical relationship. So now we have analyzed finite, linear, finite, regular, linear, context free and context sensitive. So now all the thick lines denote strict inclusion. This dotted line may or may not, it's not, it's still open problem, and all the dotted lines are the results which has been obtained by me for this paper. And for SBAC of regular and MSBAC of regular, we have just given a question mark because we are able to prove MSBAC of regular minus SBAC of regular, but the reverse we are not able to prove it, so we are just giving it as an open problem. So in this paper we have obtained 1, 2, 3, 4, 5, 6, 7 theorems, and the first theorem, the reverse part we are not able to prove, we are just giving it as an open problem.
You have a question mark on
that SBAC and maximal global.
Why do you have?
No, we were not, only one part of we are able to prove. The reverse part, I'll go back to this.
Okay, is the question where the subset is 3?
Yeah, of course. I see now. Yeah, we are not able to, this is the one we have proved actually. The reverse, we are not, it's still open problem. We are not able to give a rigid conclusion.
But you have dashed arrow in different part of the diagram, and it means the open question, as I understood.
Yeah, just which diagram, sir? Which one? Yes, sir. Yeah.
Between ICC fin and ML ICC fin, it's also open.
No, so it says ICC finite. They have proved this one part. The reverse part they are not able to prove it. Still, it's an open problem left out.
But this dashed line in this question mark has a same.
Yeah, same. Yeah, both are same actually.
You have inclusion, but you don't have
strict inclusion. Strict inclusion is still open.
And question mark means that you don't know.
We don't know the relation. Whether it is even stricter also we don't know.
I see.
That's the reason we have left it as an open problem. And day before yesterday, I got one idea whether we can leave it as an open problem. At least I can give some sort of affirmative statement. I don't know. I must want to present and I must want to verify whether that can be left as an open problem or still I can work something on that. Yeah.
So,
yeah.
What kind of parsing algorithm?
Parsing algorithm. Still, we have defined one automata for this. So KQ self-modifying weighted automata for SBAC of grammars, but we are not able to fix it time complexity of that automata. So actually we have presented, and still I am working on that issue also. Whether we can use early parsing or we can go for CVK algorithm or extended LR parsing method. Still, that is also one of the future work which I am working on right now. And still, after this, still some more results is there. I'll just go through that. So apart from that, I have solved some more closure properties also. The family of SBAC finite is not closed under clean plus, not closed under intersection, not closed under concatenation. It's not even closed under regular intersection. And SBAC of regular is not closed under intersection. So I'll just give, I will not give the complete proof. I'll just give the idea. So the family of SBAC with finite choice is not under clean plus. The logic is quite simple. Let us take L2. So this language can be generated by SBAC of finite. But if I am taking closure of that, you cannot generate this because just now only I have proved. So obviously you can conclude SBAC of finite choice is not closed under clean plus. Again, based on that first closure property, we can prove the second. Your concatenation is nothing but I'm going to do that clean closure n number of times. So obviously, if L dot L is in S base F finite, L dot L is also should be in S base F, which is nothing but clean plus, which exactly contradicts. So obviously, you can conclude family of SB's finite choice is not closed under concatenation. And the next one,
sorry,
yes sir.
I don't understand. You have a series of results.
Yes sir. Yeah.
L is
Yeah.
an SBC, L is an SBC.
Yeah.
All these results don't imply that L plus is.
No sir, you can take any language. You can take the above language also, sir. You can take any language. See,
Yes,
you are
but grammars for each power may grow and grow, and it's possible that you cannot obtain in the limit one grammar.
Sir, despite of that grammar, the language is same, no sir. You can take any number of grammars, doesn't matter. I am talking only on the language. You can take, see, for one language there can be any number of grammars.
Yes, but
yeah.
If LLL is in SBC fin, it means that there is a grammar such that it generates LLL.
Yeah, of course we can prove
And
that.
another grammar generates L in the power 4.
Yeah.
Another grammar generates L to the power 10. But all these grammars may differ. And why do you conclude that L plus is also generated by some grammar?
No sir, if that is the case, the first one should be true, no sir. If that is the case, then my SBSF finite should be closed under clean plus. But just before only I given one argument, it's not under clean plus. It's something like context-free grammars are closed under intersection.
I don't understand. Well, so maybe I don't understand.
Let me just give a simple argument against your claim. So if we take languages of star height 1,
Yeah.
like not general star height, but just star height.
Yeah.
Like we have A star, B star, A star, right? And these languages are closed over concatenation.
Yeah.
But they're not closed under either star or plus.
Clean plus, yeah, true.
Yeah, but so we can, from just listening to your arguments,
Yeah.
We can just apply them to regular expressions
Yeah.
of star height 1 and
Yeah.
come to contradictions. That's why we are confused. But maybe
Okay.
we shall need to see the complete proof.
Yeah.
But your arguments from this point are not convincing for us at all.
Okay, true.
Okay, so let's,
So probably I may give a detailed proof in the next lecture, or
I don't know. So let's just finish at some point.
yeah, sure.
Yeah, we should finish. But if you just claim this
Yes, sir,
and
yeah.
have some sophisticated proof, it's
Yeah.
quite possible because it's okay.
Yes, sir, sure. And SBCF finite choice is not closed under intersection. We can take two languages, A power n, B power n, C power m, and A power n, B power n, C power m. If you take a concatenation of these two, intersection of these two, I am going to get A power n, B power n, C power n. Just now only we have proved this language cannot be generated by SBACF finite. And same case, okay, I am going to take a language L14 equal to A, B to the plus, and I am going to take a regular language A star, B star to the plus. If I am going to make an intersection, obviously I am going to get a language L3, which earlier we have proved that it cannot be generated by SBACF finite. And the last proof, okay, a last closure property is the family of family SBAC with regular choice is not even closed under intersection. Again, we can take the same language A power n, B power n, C power n, D power m, A power n, B power m, C power n, D power m. These two languages can be generated by SBAC maximal mode and regular choice separately. Whenever I am going to intersect these two, I am going to get a quadruple agreement language. Already we are given a proof. A power n, B power n, C power n cannot be generated by SBACF regular. So the same proof or the same argument can be even extended for a quadruple agreement language. So with this I am concluding my work, and this is the conclusion. the generative power, we have analyzed the generative power of semi-bracketed contextual grammars. We have shown that SBAC of finite is incomparable with regular, linear, ICAC of finite, MLICC of finite, MLICC of regular, and MJICC of regular, and ICC are left. And we have shown that there are some common language between these two family of languages, and we have proved that these languages are not disjoint. And finally, we have analyzed some closure properties of the family of languages generated by semi-bracketed contextual grammars and are finite and regular choice. And these results, okay, has been submitted to Acta Informatica the last month. By January 25 or 26, I submitted this work to Acta Informatica. We are waiting for the reviewer comments. And what could be the interesting future work? The first one is, recently there is one paper published by Bianca Truth in 2021. They have chosen some choices which is under the power of regular, okay, sub-regular family of languages. There are n number of families. One thing is monadal, nilpotent, combinatorial, definite, ordered, circular, suffix closed, and non-counting. So this paper, it's a recent paper published in Fundamenta Informatica. They have did extensive work, okay, and they have analyzed the generative capacity of contextual grammars with sub-regular choice. In specific, they have chosen internal contextual grammars. So now, what is the idea, what I got is, okay, what could be the generative power of bracketed grammars? So they have analyzed for ICC grammars. So what is the idea, what I got is, what could be the generative power of bracketed grammars when these selectors are chosen? So this is the first future work. And second future work is, so far, okay, there is no any work related to ambiguity issues. So till now there is no work about what level of ambiguity may be there. Okay, still analyzing the ambiguity issues of bracketed contextual grammars is an open problem. Okay, so and third one, based on the components, okay, which is used for the derivation, such as axiom, selectors, and context, various descriptional complexity measures can be introduced. Okay, so now the last part is, once if the ambiguity and the descriptional complexity is measured, a trade-off between them can be investigated. So right now, okay, I am working on this part. Okay, so how to define the complexity measures, and I am working on the ambiguity part. Once if this two is, if I am able to come up to a conclusion, so immediately I can work out how to analyze the trade-off between these two measures. So because right now I have concluded one paper on analyzing the ambiguity issues and the trade-off for insertion languages. Okay, so based on that I can inherit the idea and I can come up with a different level of ambiguities and different level of descriptional complexity measures. And once if I am able to come up with that two domains, immediately I can work on the trade-off between them. So this is one line of direction. And the other research problem I am working, what could be the generative power of these grammars when subregular families of selectors are chosen. And the third problem is, what could be the parsing algorithm for this? Whether we can use LR parsing method, SLR or LALR, that needs to be investigated. Yeah, so these are all some of the references. Yeah, with this I am concluding the one of my research work which has been carried out in the past 3 months after joining as a postdoc in our laboratory. Yeah, thank you. Thank you, sir. Thank you.
I asked all the questions that I had.
Yeah, okay.
Yeah. We have questions during the talk.
Yes, sir, sure. Any other questions in the chat, sir? Any other questions in the chat? No. Okay, sir, fine. Okay, thank you, sir. Thank you. Thanks a lot.